Alright, welcome to lesson number 2. A couple of things that we're going to talk about today: inverse functions and composite functions. Inverse functions is certainly going to be a review. Composite functions may or may not be something that is new to you, but I think they're pretty simplistic, and for both of these the name pretty much says it all. So let's go ahead and get started. Right, so looking at the function, and it's important to understand what a function means. When I see a function such as f of x is equal to 2x plus 5, what this is it's a rule. Okay, the function f takes some input value, x, and then it's going to multiply it by 2 and add 5 to it, and that's going to be your output. And so let's take a look at some different examples. Let's consider the input value of 2. Okay? And so if you apply your function f to 2, if you apply this function, what you're going to do is you're going to get some output in your range, right? Your range is the list of all your outputs. Okay? And so a way that we can write this is we can say that f, our function f, took your input value of 2 and mapped it to a corresponding output. Right? The output for f, because the function has a rule of multiplying your input by 2 and adding 5, it's going to be 2 times 2 plus 5, which is 9. And so we say that f maps 2 to the value of 9. So this point over here will be 9. And we can take a look at one more example. Let's consider the input value of 4. Okay. So if we were to input 4 to our function and we apply the function f to 4, we are going to get an output of 2 times 4, which is 8, plus 5, which is 13. Alright, so what we can write, and the way that we can write this is that our function f mapped the input value of 4 to 13. Okay? And so what you might be wondering is, if we have a function f which takes us from our domain to our range, right, which applies some rule to a domain and then outputs a value in our range, is there a function that will take us back? What would we call this function? Well, the word that we give it is inverse, and this should make sense because the inverse is going to, if you go one way, it's going to take you back, right? It's going to kind of reverse engineer the way that you got from one place to another to take you from that place you got back to where you started. And so the way that we denote the inverse of a function is by giving it a little -1 exponent. And that's going to denote the inverse. So f inverse would take 9 as an input and return 2. So the way that we can write this is f inverse will map 9 to 2. Okay? And we can say the same thing to go from 13 to 4. F inverse will map 13 back to 4. And the question is, how do we find out what this inverse rule is? How can we determine what the inverse function will be that will allow me to take some value from my range and then plug that into this inverse function and get back the corresponding value in the domain? Okay? It's essentially a way of saying, I know how to go one way, but how can I figure out how to go back? And this is actually fairly simple, right? Let's consider our function. So we have 2x plus 5. And for any x value that we input, that's going to give us the corresponding y value. So we say that it is equal to y. And what we would like is an equation, a rule, that we can do some operations to y and get back a corresponding x value. And so if we go through and we solve so that we now have x is equivalent to some value, some set of operations on y, we'll have a way of inputting some value in our range and getting back the corresponding value in our domain. So let's go ahead and do that, right? Let's go ahead and solve our existing equation into something that will allow us to create that inverse, right? To go and plug in a value from our range and then get the corresponding value in the domain. So simply solving for x by dividing, first we got to subtract. Subtract 5 on both sides. 2x is equivalent to y minus 5. Then we'll divide by 2 on both sides, or multiply by 1/2. Remember, you have to multiply everything by 1/2 here. And that will leave me with x is equal to 1/2 y, or y over 2, minus, and 5 times 1/2 is 5/2, or 2.5. So let's take stock of what we have. We now have an equation which allows us to input some value from my range, divide it by 2, subtract 2.5 from that value, and then I will have the corresponding value from the domain. In other words, I have a rule which will take me from a value in my range back to the value in the domain. And so this is the inverse function. And what you'll notice about the inverse function, f inverse, is that it takes as an input a value from the range. So you might think about writing it as f inverse of y is equal to y over 2 minus 2.5. All right. Now, there's one last thing that we need to do, and this is usually the place where a lot of math students get a little lost. So if you feel a little lost after this, don't beat yourself up about it. Take some time, maybe rewind, re-listen, and kind of just think about it and make sure that you have some clarity and some understanding before moving on. Don't let yourself be a victim of normal confusion, right? Push your way through it. So if we wanted to graph both our original function, f of x, and our inverse function, f inverse, on the same graph, well, we'd want to use the x-axis as our input axis, right, as the independent variable. And in fact, it's actually going to be advantageous for us to do that because it will allow us to see the relationship between the two functions. And so what we need to do is we need to rewrite this function as f inverse, but our input variable, we need to represent it as x. And so we're going to just kind of make that substitution. And a very clear way of seeing why we have to do that is if we look, for example, at how we wrote this rule out. We said, look, f inverse takes as an input 13 and returns back 4. And it so happens that because it's the inverse of our original function, this input value is going to be a value from our original range. Okay? And so this is the relationship that is very important to realize, which is that if we have a function, f of x, the domain and the range, we know those, then for our inverse, the domain, all the possible inputs, are going to be the range of our original function. The outputs, what your inverse function is going to output, in other words, the range of your inverse, is going to be the domain of your original function, f of x. Okay, so we can write this down. All right, for f inverse, so I'm going to say the domain of f inverse, and this is true for any inverse, the domain of your inverse is the range of your original function f. Similarly, the range of your inverse function is going to be the domain of your original function. Okay? And that is an important way of remembering that even though we are going to write f inverse of x, we just have an x there because x always represents the independent variable of a function. Okay? And so our inverse function, what it's really doing is it's taking some value that is from our original function's range, and it is telling you how to go back to the value in the domain of our original function. Okay? So now what we want to do is actually look at kind of the relationship between the original function and the inverse. And so to do that, to make it really clear, let's go ahead and graph both these functions on an xy plane. And I encourage you to go ahead and try this on your own first. So let's first graph our original function, f of x. And f of x is going to have a y-intercept at 5. 1, 2, 3, 4, 5. And it has a slope of 2, so meaning if I were to go back 1 unit to the left, I would decrease my y value by 2. I'll try and draw a straight line here. Oh boy. Well, A for effort, I guess. And now let's go ahead and graph our inverse function. So the inverse function, it has a y-intercept at negative 2.5. And a slope of 1/2, meaning that if I were to move 2 units to the right, then I would move up 1 unit. Or another way of thinking about it is if I were to move 1 unit to the right, I'd move up 1/2 unit. Simply thinking about slope as rise over run. And so let's move 2 units to the right here, and that would mean I'd move up 1 unit. Do the best I can. Probably not very good, but I'll attempt now to draw a straight line. Okay. All right, looking at these two lines, it's pretty obvious. Like there's some sort of relationship between the two, but what exactly, might I describe that relationship as being? And in order to see this relationship, we want to think about how there was a kind of shift that took us from having our original function f and then now to our inverse function f inverse. And essentially what you're thinking about is that, look, the role of x and y, the role of the original domain and original range, in other words, the domain and range of my original function, they switch roles, right? Originally, the domain was the domain, right? All the input values were the input values. But for my inverse, the input values of my inverse are actually values that are from the range of my original function, and the output are now from the domain of my original function. And why this is important is because graphically, for our original function, x represents the input values, right? And y represents the output values. And so if I wanted to take this function here and turn it into my inverse function, I would have to swap the roles of x and y axes, the x and the y axes. And so how could I do that? What would I have to do to my coordinate graph here so that all of a sudden the positive y direction is in the place of the positive x? And what this boils down to is simply reflecting over the line y equals x. If you think about it, y equals x is just a line that says y equals x. And if you reflect over it, all of a sudden the x and the y are going to be in different positions. And so I'm going to draw the line y equals x. I'm going to do the best job I can. Probably not going to be quite perfect. Something like that. This is the line y equals x. And what we can see is that if we were to reflect our original function over this line y equals x, I would end up with my inverse function. Okay? And so that is the graphical relationship between the original function, any function f of x, and its inverse function, f inverse of x. Okay? So that should make sense because the roles of x and y have shifted. And just to recap here, there's a lot that we've gone over, but this applies to pretty much any function that we are going to see. And eventually in your math career, you're going to think about some different things that don't have inverses, but we're a little ways away from that at this point. So remember, of course, that the inverse is a function which will take any original function and will allow you to map values from the range of that original function back to values of the domain of that original function. And the way that we do that is by solving for the variable that used to be the input, that used to represent the domain, and so that now we have an inverse function which allows us to take some value from our original function's range and get back out a value from the original domain. And so it's vitally important to remember that for any inverse, the domain of that inverse is the range of the original function, and that's going to come in handy, okay? And the range of our inverse is the domain of our original function. And so for this function here, that's not all that interesting, because the domain, all the possible inputs of our original function, hey, that's every real number, right? It's all real numbers. And the range is also all real numbers. So the domain and the range, it doesn't actually yield anything all that interesting, but we're going to look at some functions where the domain isn't all real numbers, and maybe the range isn't all real numbers either. And so that will give us some interesting relationships. However, no matter what the relationship is, graphically we'll always be able to represent and to show the inverse of a function by reflecting our original function, the graph of our original function, over the line y equals x. Because essentially what we're doing is to find our inverse, we are switching the roles of the input and the output, or the x and the y variables. And so by reflecting over y equals x, that line, we are going to essentially be doing that, and that will yield our inverse function. Couple things to take note of here. The first is in finding the inverse function, we're still going to follow the same process regardless of the function, right? We're going to be switching the roles of the domain and the range of our original function, in other words, x and y. And when you square root both sides of a function, after subtracting 4, when you square root both sides, remember when you square something, you're always going to get a positive value, right? That's why your square root is always positive. But you could input any value, positive or negative. So when you square root both sides, you've got to include the plus and minus. And if you were to look at x squared plus 4, maybe I'll draw us a quick sketch here. If I were to look at x squared plus 4, which looks something like this, and I were to reflect it over the line y equals x, right? When I reflect it over that line, I'm going to see that I get a function that looks like this. And notice that if I didn't have the the plus minus here, if I only had the plus, right, I would only have the square root of x minus 4, which looks something like that. And if I include the negative version, then I will also get this piece here. Okay, so that's a quick thing to keep in mind. Right? For the other functions, finding the inverse here should be pretty straightforward, as it should be here, that I'm just going to square and then add 3 to both sides. Go ahead now, and if you haven't already, identify the domain and range for each. Remember that relationship that we discussed previously. That will be very helpful. Alright, so here you have them. Notice that you shouldn't be doing a ton of work for these. You should be thinking about the domain and range for your original function, and then realize that for the inverse, the domain is the range of the original function, and the range is the domain. And so you can go back and actually look at the relationship to kind of make sure that it's correct. And so one really clear example is looking at these two and noticing, look, for this function here, I can plug in any x value I want. So my domain is all real numbers from negative infinity to positive infinity. But the range, it's not going to give me every possible output, right? Because the smallest output that I could possibly have is 4, right? Because when I square something, the smallest value I could ever get is 0. And so my range is going to be from 4 to positive infinity. And the inverse function is a square root function. So I actually can't have a domain of all real numbers. The smallest domain value I could have is 4, because then I have the square root of 0. And so my domain should be from 4 to infinity, which is of course the range of my original function. Okay, so hopefully you're getting some good work with that. Some extra practice and a good idea might be to go through and graph each of these functions and then sketch a graph of what the inverse should look like without looking back at the inverse, right? So knowing just that I'm reflecting over a certain straight line. Alright, so this is what's called a composite function. It's a function that's made up of two different functions. So notice that f of x takes an input and squares it. G of x takes an input, uses that as an input for sine, takes the sine of that value, and then adds 2 to it. So when I read this function here, what I need to recognize is that the input of my function f is the value after I input pi over 2 into my function g. It's kind of like unpeeling an onion, right? There's many layers. And what we've got to get to is we've got to do the innermost layer first. So first you must evaluate g, your function g, with an input of pi over 2. When you do that, sine of pi over 2 is 1, plus 2 is 3. So this value here is 3. So then you're going to evaluate your function f with an input of 3, and 3 squared is, of course, 9. So a composite function really just refers to the combining of functions where the output from one function is then the input for your next function. And there are a couple of ways that we can represent this. There's what's called a composition notation, and the way this would look is f, and this is the composition symbol, f of g of x. That's one way of writing it. And an equivalent way of writing it would be to say f of g of x. Okay? And either way, so the way that we could say this is we could say f composed with g of x, and here you would say f of g of x. Personally, I like this notation much more because it's very clear which one we evaluate first, right? G of x is the input for f of x. and this is going to just lend itself a little more clearly. But if you ever see this, you'll know what it means. And so this, the way that we say this again, is f of g of x. I'll actually write this right here. F of g of x. And I like to use the analogy of an onion, so to speak, in that an onion has many different layers, okay? And the composite function has many different layers, and you always want to work with the innermost layer first. And so in this situation, the innermost layer, right, is g of x. And so you have to input the value of x into your function g, and then whatever you get out of that, the output from g is going to be the input for f. Now the outputs of a function are known as the range, and so the range of g of x is going to function as the domain for f of x in this function f of g of x. And that should make sense, right? Because for this function, the only values that you'll be able to input for f are values that you can get from g, meaning that the domain of f of x is the range of g of x. Or another way of saying that would be that the range of the innermost function is the domain of the next function. Okay, so that's actually something that I would probably include here. And so this might at first seem a little strange, but I think it's actually very straightforward. And if you always keep in mind the onion, and always remember to go from the inside to the outside. So looking at this f of g of x, you're going to work with g of x first, and whatever you get from g of x, you're going to plug into your function f of x, and so on and so forth. So let's actually practice writing a composite function. So let's say, for example, we have f of x is e to the x, and g of x is negative sine of x. So let's try composing the functions in two different ways. So first, we'll write f of g of x. Encourage you to try that one on your own. So remember, f of g of x means that g of x, whatever that function is, whatever that output is going to be the input of our function f. So thinking about g of x, it's going to give you an output of negative sine of x. Notice whatever that input is there. And so your output is going to be when you take the sine of that value and multiply it by a negative. So this is going to be the output that g of x gives us, and we need to use that as the input for f of x. And so what f of x will do is it will take its input and it will use it as the exponent with a base of e. So we're going to take the output of g and use it as the exponent with a base of e. E to the negative sine of x. You could take a look at that function, maybe graph it on Wolfram Alpha. Okay. Now let's try the other way around. So let's do g of f of x. So now the output that we get from f, which is e to the x, is going to be the input for my function g. So g will take its input and we'll use it as an argument for sine and then multiply by a negative. So when it takes the input of f of x, well, f of x is e to the x. So now e to the x is going to be the input of our function g, and we will end up with negative sine of e to the x. Both functions kind of a little funky, but we're going to see some interesting functions, and that is kind of how a lot of mathematics requires that we're very quick with some kind of interesting functions, because we never know when we'll need to compose them in a way that will enable us to model real life more accurately. And just in case you decided not to, I went ahead and graphed both these functions on Wolfram Alpha so we can take a look at what their graphical representation is. So here we have it. You'll notice that they're color-coded down here. So the blue function is e to the negative sine of x, which is f of g of x. And the red function is negative sine of e to the x. And so you'll notice that this is a really funky looking function, which is interesting. Yeah, so we can create some really cool functions using compositions. They're fairly straightforward. I'll give you a couple to practice with, and then we'll kind of use them throughout, and they come in handy in calculus, especially later on when we start doing some more complicated things. Alright, so here are the answers. Should be pretty straightforward. A couple things to notice. Distribute the negative in. Make sure that you're not forgetting to do that, right? It's minus x, negative x, so your entire input is multiplied by a negative. And then this last one here, it seems daunting at first until you realize that you've already found f of g of x. And so you can think of this as being a function you've already found, this piece right here, and so you're just composing that function with h. Or you can go from scratch, and that might be a little harder to think about, but you could do it, right? And you'll essentially go through the same process where you compose f and g and then compose that whole thing with h, right? But so notice here, f of g of x is e to the negative square root of x plus 2. And so I take this function now as the input of h, and h is cosine of 2x minus 2, and so now I have 2 times e to the negative square root of x plus 2 as the input of cosine. One last thing to notice is that it would be good practice to try finding the domain of each of these functions. So if I gave you this function, I said, what is the domain of this function? You realize that the domain of this function is g of x, right? Whatever values g of x could be. And so the domain of this composite function is, in fact, the output or the range of g of x. And so if you look at g of x, you realize that this can have an output of anything from 0 on to positive infinity. So you can input anything from 0 on to positive infinity into your function f of g of x.